Hi, I'm Ethan Cecchetti. I'm a PhD student at Cornell. This is uh, definitely not fully baked, but partially baked work that I'm doing with some collaborators, a couple of other grad students at Cornell, and my advisor, Andrew Myers. Um, so I want to start by introducing what the idea of reentrancy is. So let's take, for example, a simple bank on a cryptocurrency, something like Ethereum. And so it's going to hold a giant pile of money, and the giant pile of money is going to be owned by collectively a bunch of different people. So it also wants to hold on to the account balances of all of those different people. And people might want to take their money out of the bank, so it has some steps to withdraw money. The first thing it's going to do is it's going to check to make sure that you have the money that you're asking to withdraw. Then it's going to send the money over to the recipient and alert them to the fact that they got the money and essentially wait for a confirmation. From a technical standpoint, this is basically just done on a blockchain system using a synchronous function call, but we can think of it as just waiting for confirmation. And then once it's confirmed that you've received the money, it decreases your balance accordingly. So maybe Bob wants to withdraw $10 from the bank, so it requests $10. We check the balance. According to the balances, Bob has $20, so this is fine, no problem. We ship $10 over to Bob, and we wait for Bob to alert us that he's received the money. If Bob's behaving properly, he's just going to pocket the money and then return back, sort of alerting us that he's successfully received it. We can reduce Bob's balance to $10, and everything works great. The problem comes in when Bob is not so benevolent, and Bob is actually trying to attack our bank and comes up with a brilliant idea that what he's going to do is he's going to start by asking for $10. We're going to run through the same step. Yep, we've got $10. Send him $10 and wait for a response. But Bob, instead of pocketing his $10 and confirming that he got it, is going to just ask for $10 again. So what do? We go through the steps. We check that he's got $10. Well, we didn't change his balance, so it looks like he has $10. We send him $10, and we wait for a response. Bob can just keep doing this over and over and over again until he's not only withdrawn more than his entire balance, he's withdrawn $50 million more than his entire balance. And this isn't just an arbitrary Ethereum bank. It's something called the Decentralized Autonomous Organization, or the DAO, which you may have heard of. And this actually happened. Ethereum had a hard fork to undo the problem in July of 2016. It made national news in multiple different places. And so we'd like to be able to avoid this kind of problem. I work on information flow control systems, particularly static information flow type systems. And so information flow seems like an obvious way to get rid of this danger. We're going to tag how trustworthy things are. This is oftentimes information flow is done to preserve confidentiality and stop data leakage, but there's also a lot of work, particularly in the static information flow space, to preserve integrity of systems. And so we're just going to use integrity here. We can tag the money in these account balances as being trustworthy, and we can tag Bob as being untrustworthy. And normally an information flow system is going to require that if we're executing trustworthy code, we have to have come from a trustworthy context. So when Bob sends this second request to try to get $10, we're going to stop him and say, no, you're untrustworthy. You don't get to access this trustworthy code. So this seems like it should solve the problem until we back up a couple steps and realize that the first withdrawal request, where Bob was trying to legitimately get his $10 out, also gets blocked. And since I'm only giving a 5-minute talk, I'm not going to go into way too much detail of how we fix this. But the takeaway here is that standard information flow techniques don't so much solve this problem, is they allow us to identify the critical sections of the code. They allow us to identify what we need to make sure doesn't get interrupted, needs to execute atomically. This connects a lot with some other work that people have done on reentrancy, viewing it similar to concurrency problems. And the work that we've been doing, which I'm happy to talk about in more detail offline, is basically how do we allow that first withdrawal call in while not allowing the second one to happen midstream, treating this withdrawal operation as essentially an atomic block. and using information flow techniques to do it. So that is almost exactly 5 minutes, and I would love to take questions.
Questions?
Okay. Thanks. Thank you for the talk. So this sounds like if you're doing information flow with types, if types change across the execution, it seems like that might work. So is this session type based?
No. So there's actually one of the things I've talked to some people about is if you use linear session types, it's unclear that any of this is really truly a problem, because if you want to do something that would be dangerous in a reentrant execution, you would essentially have to prove that you only use the thing once in the combined execution, and so you're probably fine. We're not using linear session types, partially because we want to fit in better with the sort of mental programming models that people are already using, and bolt something comparatively easy to understand on top of it, and still allow, basically optimally, if somebody writes a secure program right now, we'd like to be able to slap this on top of it, basically run a type checker with a couple of extra annotations and say, yes, this is secure, in contexts where there's no way to make it type using a linear type system.
I see. Okay, thank you.
Yeah.
There was another question? Oh. Okay.
Certainly sounds like session types, but yeah, you're right about the difficulty of using it.
Yeah.
Other questions? Okay, let's thank Ethan.